All right, I think we are up and going. All right, well, welcome to, I think we're in week 3 now. So we're trucking along through winter quarter. Um, as I noted on Canvas, and as you've no doubt figured out, we are remaining online this week, and I'm just kind of like going to make a blanket policy of doing this class remotely until further notice. And I want to see what this week's dashboard at Clark looks like. They're only updating it once a week, unfortunately, and it's not till late on Tuesdays, so that's tricky.
I'm kind of curious. I feel like Zoom is like the perfect way to do this class because you can also follow along on your computer.
Mm-hmm.
In person, do you just have like a big projector and you go through?
Yeah, and
Like on a projector?
it's kind of been a challenge for me from the start, because during class I would actually like students to be able to have online access, so that in the classroom we could actually like work on problems together. Or I could give things for people to try and so on. And in the past, we just didn't have the network infrastructure to support a room full of people being online. That may have improved at this point. They apparently were going to make some changes to where the routers were in the STEM building and so on. Partially, in support of zooming from the classroom and such. But yeah, I like the online format for having access to the computer and so on. But what I don't like, and what I think some other people don't like, is just the fact that a remote experience is not the same as a face to face. And I can talk for 20 minutes and have no idea if people are understanding what I'm getting, if they're struggling, or if they've just given up and gone on to something else. And in the classroom, I didn't realize it when I was teaching in person, but I can usually tell pretty quickly what's going on, sort of with the class at large and with individuals. And if there's questions, I don't need somebody to raise their hand and say, I'm confused about this. I can kind of tell. And I miss that.
Blank stare.
Yeah, yeah.
I don't know. I feel like because I've only done remote. I started in summer last year.
Right.
I feel like if I don't understand something, it's easy enough for me to just ask a question.
Mm-hmm. But
sometimes people are different.
Sometimes, if we're going over something new in particular, right, it may be the case that one does not understand what's going on, what we're talking about, but can't necessarily formulate a question, right? Particularly if something's making no sense at all, or if I've forgotten to describe some piece of critical information that sets this up. It may just be general, like, this is not making any sense, I'm going to have to watch the video later. And I can usually pick up on that pretty quickly and say, oh, I should have said such and such. So yeah, hopefully we'll get there. WSU Vancouver's numbers, I looked at their dashboard and they actually look pretty good. They've had fewer than 10 cases at the Vancouver site, at least that are reported. And Clark's dashboard kind of blew up last week. I've got students who have either tested positive or have been exposed. I'm in a musical group, and we had 2 members test positive last week, and I mean it's not a good time right now. So we're gonna make do with what we have and stay remote for now.
I've been in kind of a sticky situation with my physics class.
Yeah.
Where there's only the option for in person, but we had to quarantine for 2 weeks because 3 people tested positive, and
Wow.
my family's kind of barring me from in-person stuff, so
Yeah, yeah.
I kind of don't know what I'm doing right now.
Yeah, that's a quandary. Yeah, I don't know what to say about that.
He says he might make an accommodation for a few students, which is good, but
Yeah, so definitely go to Clark's website, look at the COVID information. I know there's so much information, sometimes it's hard to find anything in particular. But see what the school's policy is on accommodations for students who are in an in-person class. There's risk factors and what can be done in that case. And I'm definitely trying to be flexible with students. I mean, a lot of people live with, older parents and things like that. And, yeah, you don't want to take chances. And yeah, it is really difficult to get tests right now. So if you don't know, the government just opened up their program where they will send you 4 free tests per address. And it's through a USPS site. So I saw something earlier today and I hopped on the site and just put in my name, address, and checked a box. And supposedly 4 tests will be sent sometime in January. We don't know how accurate these are, depending on what kind of COVID you're testing for and how long ago the exposure was and so on. But, it's presumably better than nothing. All right, so questions. I'll talk a little bit about PA1, but any other questions up front first? We were talking about stacks and a little bit about queues last week. And we're going to mostly continue that this week.
I don't think we actually got the keys, by the way.
Yeah, I think I used the word and that was it.
Yeah.
All right. Well, let me talk a little about PA1 then. PA1 was a pretty good experience for many people, I think. Some people just ripped through it right away, but the majority of people had to work pretty hard. But from the people I've talked to, it sounds like on the other side, life does get better. Having figured out, the peculiar bugs of one's own programs. On the other side of that, there's, a better understanding of dynamic memory and, mallocs and frees and dereferencing pointers and all that sort of stuff, in addition to, learning about linked lists. And so, let me take a look at the grading. So you saw the grading rubric right before before you started working on the assignment, and this pretty much governed how I graded your assignments. Let's see. I've decided even if I finish the assignments early, it's still better to turn in a few days later so you can catch your errors. And we talked about assignments in the lecture. Well, that's true, but you can resubmit. Until the deadline. Once the deadline hits, whatever is submitted, as soon as it's submitted, that's what I'll grade. But if you submit something on Wednesday and then you decide to make a change, you can resubmit it on Thursday, and that doesn't cost you anything. Because I don't download anything until Friday at 8. All I'm trying to avoid is downloading programs and grading them and posting grades and then having someone come back and say, oh, don't grade that one, I'm using slip days right now, and then it's an unfair situation. But before the deadline, you can go ahead and resubmit if you like. So let me just talk about this. So a few cases of corrupted tar files. You're going to be probably turning in all your code through tar files, probably also for CSE223 in spring. So you definitely want to get good with tar. And I gave you a command in here for building your archive. So, yeah, go ahead.
I just remembered I had one question.
Yeah, go for it.
And it's a makefile question.
Mm-hmm.
So, when I was developing my code, I made a target for debug.
Good.
Also.
Okay.
And two questions I have here is, one, I couldn't actually get the debug files to the debug target to make unless I use the actual C files. This says the object files. Is that normal?
No, you should be able to say make debug and it'll follow that recipe instead of whatever the first recipe is. And it should be able to recompile and all of that stuff. But if you've built your program and then you try to make debug and you haven't changed anything, it may say everything is up to date. Is that true?
Yeah, but when I try to, it'll actually make the debug target if I have all the object files and I compile it that way. But every time I go into GDB, it's giving me the symbols not loaded.
Oh, interesting. Let me see. Oh, you also have to compile with a -G switch, I believe.
I was. It's just for some reason I could only get it to work if I input the straight C files. And my other question was, when I clean it, I always get an error of there is no debug file if I cleaned it and there was no debug file.
Okay. So
is there any way to avoid that?
Are you okay if I put your make file on the screen?
Absolutely, go ahead.
All right. So so for main, you're saying that in order to build main, you need functions.o and main.o. That's correct. But for debug, you're indicating that you only need functions.c and main.c. And then gcc-g this -o debug. That should definitely build a debug executable, but it will only do it if you've modified functions.o and main.c.
Right. Interesting.
So I can do the regular make, I can say make debug, and that works fine. And then if I say make debug, no, that seems to actually work. If I do this again, right, it's going to be up to date. If I touch main.c, it should go ahead and recompile into an executable. So actually that seems to work for me.
I wanted to use the object file, but for some reason every time I did, it just wouldn't load the symbols.
So, so something like that.
Yeah, like that.
All right, but you have to put the -G switch in your .c compiles also.
Oh.
Yeah, because that's where the symbols come from, is the source code.
I gotcha.
Cool.
Thank you.
And then this right, so if I say make and then I say make clean, it'll complain that the recipe failed because it couldn't remove debug, right? Because I didn't make a debug. So what you can do is you can say rm-f, and that will forcibly remove these files, and if they don't exist, it will simply continue without complaint. The only trick is if you try to, like, you know, write protect one of these files, the -f will override that protection. So if I say make clean, I can do that a million times and it won't complain.
Is there any way to make the object files compile without the debug and with the debug if I need to make the debug? So there's like, you know how like if a debug is always a little bit slower than the release because of the debugging information? Right? Is there any way to make like a release version?
Well, so I mean, you can start getting right. I could say that my debug depends on dfunctions.o and dmain.o, and then I could make a dmain.o that's built like this, and a dfunctions.o, and these I would put the -g switch, and I think that would work. I shouldn't have tried running it. I should have just left it. I don't know if this is legal or not. Yeah, that seems to work. And you'd want to change your clean to get rid of the debug versions of the objects also.
Well, that's cool. Thank you.
Yeah, yeah. Although I think what you did was probably the best, which is for debug, just go ahead and slap the .c files together, because you're probably not too worried about efficiency for that case. But if you were, if you had a lot of files, yeah, this something like this would work. Cool. Thanks for sharing your code. All right. So yeah, PA1. Make sure you know how to do a tar file, and if you don't, or if you ran into a problem with it, definitely come by and let's figure this out. And remember, you can easily corrupt your files by doing this incorrectly. If you forget to put pa1.tar here, and you just did tar cvf main.c, that will destroy main.c, and it's unrecoverable. You have to go to a backup to get it back. So be careful with this tar command, right? And I always recommend, you know, have the area that you're working on, well, have backups. That's the main thing I recommend. But, you know, if you're going to mess around with tar and stuff, copy everything over somewhere else and work in that other directory. And then, you know, you can tar xvf to extract from the tar file, so that once you've got your file that you're ready to upload, copy it into a new directory. Do tar xvf, do make, run your test cases, make sure all of that works. Right, and that's a good sort of acid test for the file I'm going to upload is, you know, the one that I want graded, and it should work. So that's a biggie if you know, I can't get to your files, if there's files missing, and so on. If it does not compile, and there were a few cases of this where there were compile errors and it wouldn't build an executable, but I was able to go in and fix those errors and then test the rest of the code. So that's not something that's always an option, but it was for this one. Any deviation from the prescribed function names, prototype, struct, mynode, etc., 50%. And in some cases, I back that down to 25% deduction. But I'm being dogmatic here for a reason. The main goal of this assignment, of this course, of the sequence at Clark, right, of getting a degree in computer science, is to be able to program, to be able to debug, to be able to make linked lists, understand linked lists, and so on. But there's another really important aspect, which is being able to follow a specification to the letter, right? And I've known, you know, cases where people spent, you know, a good part of a year working on a project and coming up with the final deliverable, and the deliverable had to be named a certain way, and when they submitted it, it was named incorrectly, and the system rejected it, and all the work that they had put in led to nothing because the place they were sending it didn't accept it. And you'll find this, you know, with university classes where there's automated grading. You're told, you know, you have to name this file with your last name, underscore, first initial, period, blah, 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 right? And if you don't do that and you submit it, the system just dumps it. And you look at your grade the next week and it's a 0. So I was being really, really picky about, you know, the stuff that I spelled out on the requirements. So making sure that you have a struct mynode, making sure that you have these 6 functions, making sure these are in a functions.c, making sure your main program is in a main.c. That was the program structure section, and a makefile in main.h. So I took off a bunch of points for that. Same thing here, same thing here. All right, makefile. Most of the makefiles look good. That was great because it's nice to be able to just say make and go ahead and have your program be built. One comment on the make clean option, right? Don't just rm start auto, right? That's a really dangerous thing to do. Using wildcards with rm, you can do that yourself in your own directory if you're really sure that's what you want to do, and or you're willing to take a risk. But don't ever give a file to somebody that's going to rm star, right? Because if they run that from a different directory where they've got their own object files, you might wipe out their object files. And if they do that, they're never going to download your code again. They're going to say like, oh, stay away from Nick's code. He's got this crazy clean function that wiped out my whole directory. So be tactical, right? And the idea of a makefile is, you're not just saying gcc star.c. You're very, very carefully compiling the exact pieces that you need to create an object, and then to create those objects and turn them into an executable. And so your clean should be as delicate, as precise, right? Get rid of the pieces that your makefile will create if you want to allow the person to force a recompile of everything. And this is useful, for example, if you have a package that you put in the tar file and it's already got executable code in it, but it was compiled for a different machine, right? Or I've got this code running on my laptop, it works great, I want to just take it all and shove the code over to my Raspberry Pi and recompile it. Well, if I put all this code on my Raspberry Pi and I say make, it's going to say everything's up to date. So I've got to get rid of the objects to force GCC to rerun, because it's going to make different, compiled code on a different CPU. So a make clean lets you prepare it so that make will recompile everything.
I can imagine that remove star. That I don't know why, but I got a big laugh out of that, because I can imagine someone downloading into like one of their project files and then deleting everything.
Yeah, yeah.
What happened?
Right. Yeah, and I've gotten burned by that too. And I've gotten burned sometimes by doing that myself, by having, something that's supposed to clean stuff up, and I forget that I'm in a different directory, and I run this code, and there it goes.
I can see that being a fun prank in university.
Yeah, yeah. All right. All right. So init, print, and search. I'm thinking back because I'm wondering if that's ever happened. But yeah, don't do that. Init, print, and search. So not a lot of issues with that. One thing I'll mention, in some cases, people are still doing this thing. Right? I'm going to say never, ever, ever, ever do that. Right? If list is a pointer to a structure and that structure has a field named data, always do this. Stick with the arrow notation. For a few reasons. One, if you do something like this in a job interview, they're going to wonder if you understand this. And if they think maybe you don't understand this, they're probably not going to be very interested in hiring you. Number two, if you do this, it is going to confuse anybody who's trying to read your code, because almost everybody who's experienced with dereferencing pointers to structures understands this. It goes directly into your brain as this is the data field of the thing list points to, whereas this, has to be interpreted. It's like writing poetry backwards. It's not the same experience in your head. So avoid that. Do this. The other thing is that when we get into structures that contain pointers to other structures, this is going to get really cumbersome, and this is going to be very, very fluid. So keep that in mind. I didn't take off points for that, but if I noticed it in the code, I put a comment in there, so that's what that's about. So add and delete were the trickiest, right? And the main tricks with adding is skipping the sentinel, right? Making sure you start with the thing that comes after it. making sure you don't fall off the end of the list, stopping before you get to a seg fault, and dealing with the case where you have to add to the end of the list. The number you're putting in is bigger than any number you found. And that third case is the most critical because that's the case when you have an empty list. When you have an empty list, your while loop will kick out immediately and you have to add stuff at the end.
Yeah, I think that was the hardest for me, was thinking about that, going, why is it kicking out of the while loop so early?
Right, right.
And then once you figure that out, it's like, oh, that's what you do.
Right, right.
I think GDB showed me that.
Yeah, GDB is nice for that. Like I say, if you can step through and if you know what your code's supposed to be doing, you can follow along in the source code. It will help you figure out where something's going wonky.
And GDB is kind of a basic debugger, right? Like, once we get into university, we'll be using a few more programs that are a little more powerful, right?
Well, GDB is yeah, it's kind of like the assembly language of debugging, and within GDB you can define macros and all kinds of things that will make it look a lot fancier, and do a lot more for you. You can have it automatically do things after each command and so on and so forth. But beyond GDB, right? If you get into something like Eclipse or IntelliJ or things like that, these integrated environments usually have their own debugging system also, and those will get into graphical stuff and color coding and all the good whoozits that people like.
I didn't know Eclipse did C. I'm using it for my Java class at Bellevue College right now. And
Okay.
I'll have to check it out. So that one you can actually step through, and it's kind of like the one we use for engineering. Right?
Okay.
So it shows you the variables on the side.
Yeah. And Eclipse does C, but I don't know if it does C very well. I played with it when I started teaching some of the C classes, and it works great for Java. As far as entering code and compiling and so on. I got the feeling it wasn't quite as tuned for C.
Okay.
But yeah, give it a shot. See what you think.
Alright, I'll check it out.
Yeah.
If you use Visual Studio Code, you can use GDB in a more graphical environment.
Okay.
Maybe that might help you to see like all the features you might be missing out on, or just it wasn't immediately clear to you that you could do in command line.
Yeah, that makes sense.
Command line.
Mm-hmm.
Yeah, I liked an engineering class where you're actually watching the variable change, like as you're stepping through the code and stuff.
Right, right.
I like that kind of thing. Instead of going, oh, what is it now? What is it?
Right.
You can just see it change and go, okay, that's where it's supposed to change. Perfect.
Yeah, and MPASM makes that nice. And you can set up watches for variables. You can watch program memory. You can do all kinds of stuff. And yeah, that's definitely nice. Like I say, there's definitely ways to get GDB to do more. The way we're using it from the command line with just simple commands and examines and prints and so on is kind of like doing assembly language. It's very low level interaction, and you can definitely augment it.
So it's a very broad program. You just have to set it up that way.
Right, right.
Gotcha. Okay.
You can also you can set different layouts. Like if you say layout space ASM, it'll throw you in an assembly language layout, and that'll actually show you your registers on the top half of the screen, and they'll change dynamically as your program executes and so on and so forth. It's pretty fun.
That's cool. I'll have to check that out.
Yeah, that's layout ASM. All right. Main program. Main program is only worth 10%, right? So some people who are struggling with main, I told them, like, write your own main program, lose the 10 points, but use that to, develop your other functions and be sure that your other functions work. Make sure your commenting is good. There's no memory leaks, all that kind of stuff, right? And then I had my own main program that I linked in to further test your linked list package. But main program, is 224 stuff. It's parsing the input. It's checking, for a legal integer, extra stuff after the integer. all of that usual business, and so most people main program looked fine.
And did you use your main program just to make sure that it is a good working program, just in case ours was the problem?
Mm-hmm.
Is that why? Okay.
Yeah, I used my own so that I could have a bunch of adds and deletes and searches and looks for memory leaks and things like that, without having to type them in every time. And also to ensure that your add function was called add, your node was called a my node, that kind of stuff.
Gotcha.
Memory leaks, Valgrind errors, warnings. Did not see a lot of Valgrind warnings, which is great. And I'm kind of hoping that that's because people got warnings and they figured out how to get rid of them. But if you got lucky and just never saw warnings, that's okay too. But yeah, almost no warnings. A few memory leaks, but happily almost all the PA1s freed up all their memory when exiting, which was great. Almost no compiler warnings, which is great. And then commenting, and most people lost some points on commenting. So there were 4 commenting points. The first was, before each function, having a block that clearly explains the function in detail, right, as described above. So you've got a function that adds a node to a list, right? What does this do? Well, you need to comment more than add a node to the list, right? Your add function takes 2 arguments. What are those arguments, right? What do they mean? Your function returns an integer. What's the value of that integer mean? What does it mean when you say this adds this to a list? It adds it in increasing order. What does that mean? So having a block of comments before each function that makes it clear what's going on. A comment block in the beginning of your main program, which has your name, the date, and a synopsis of the program. And as I said in the assignment, it's got to say more than linked list program or PA1. It should say basically what the program does, and then commenting throughout the code, and anything that's not completely obvious what the code is doing, put comments in there. Explain why you're setting previous next node equal to current, right? That doesn't mean anything if you just look at that statement. So what is that? What is previous next node? What is current? Why am I setting the former equal to the latter, and so on? And then consistent indenting of code, and this is your choice of what style you want to use, but use it consistently. And it definitely ran into cases where there were nesting errors, there were logic errors, you were returning too soon in a loop, or you were trying to do something outside an if statement and you wanted to do it inside. And in some of those cases, right, the indenting was not consistent. And if you made it consistent, it was a lot easier to look at it and see, oh, my return statement is, it's outside of my if, or my assignment statement is inside my if, and it should have been outside. So minor details like that. Let's see, isn't it always, there's a question and comment, isn't it always a safe bet to try to not use raw pointer syntax when possible, even for arrays? I would say especially for arrays. But no, I mean, you can use pointer syntax, things with stars and so on. It's mainly when you're dereferencing a field in something that is a structure that's being pointed to. It's just, this is the preferred way to do it. And if you're passing, an integer by reference or something, you kind of have to use star argument as a way to get to it. And yeah, that's usually okay. All right. Let me just hop into some sample code. Let's see. So just an example of of what this might look like. So so the makefile, this is pretty much what most people's makefile looked like. Because I forced you to use these names for your files, so not a whole lot of flexibility there. My include file was just, you know, the definition of a my node and some function prototypes, and I should have put some comments in the top. I didn't. I typed this up last night at like 10 p.m., so I kind of rushed through it. But I did put comments in my C files. So here's my main program, right? So I'm including main.h, right, which pulls in that source code. And by the way, when you compile, you don't compile main.h. You list main.h as a dependency, but you don't give main.h to a GCC command, right? That's not something we do. Because we're trying to compile, you know, functions.c, that's fine. If we try to compile main.h, well, there's really no executable code in there. Thank you. It's stuff that makes sense if we include it inside functions.c. But if you try to compile it, you get this weird GH file or something like that. So we don't list it on the actual GCC line. So, you know, here's my attempt at a blurb in the front to keep my teacher happy, with the assignment name, the date, my name. Use your full name though. And what the heck is this program? It's a linked list package plus a main program. It lets you do these things. The user interacts with a series of simple one-line commands. Here's a really brief, you know, sentence fragment description of each. My user added to the list, so the list is always sorted. So something like that. Let's see. I see lots of banter between C programmers and whether to denote an array, bracket, bracket, or star array. There are differences between those, and I'm not confidently versed in what exactly the differences are. But I can tell you, I've never used array, bracket, bracket in my life. If I declare an array to have 100 elements, I'll say, you know, int data bracket 100. If I'm passing an array and I'm writing the function that receives it, I'll say int star array to say this is you know, pointing to an int or whatever. And I've lived so far without having to say array bracket bracket. So I'm guessing maybe my life would be 10 times better if I did that, but I'm guessing not. But I know there's cases where array bracket bracket seems to get the compiler unhappy. Off topic, what kind of fountain pen do you use? I have a whole slew of fountain pens, and most of them are inexpensive Amazon purchases. There's a few that are a little higher caliber, but I don't know. I like Schaefer's. They're nice and reliable. And I really like Parker's. Is there any good document you could recommend on makefiles? So if you look at the alternate text on Canvas, it's got, I think, a section of a chapter on makefiles that I just show you a basic makefile, I think. Double check that. If not, let me know. But pretty much, you know, this is all you need. Target and dependencies, and then a recipe for building the target. Target and dependencies, and a recipe for building the target. And maybe a clean. Alright, so what's the main program do? So I like small main programs, so here's my whole main program. So I call the initialize function to create an empty linked list. I print a prompt, and then I have a while loop. My while loop you can also exit with Control D. That wasn't required. But I basically read a line of input from the user, I save it in buffer, and then I call this process function. And process is a super function that basically processes the input, looks to see what command is being requested, checks the syntax, and if the command is legal, executes it. and it returns a flag saying should I continue looping or not. And basically, if it processes the X command, it'll return 0, otherwise it'll return 1. So if process returns 0, I'll say break, otherwise I'll print a prompt and go back up to the top. When I break out of the loop, it means process saw the X command, I call my cleanup, and I'm done. And then all this funny business with scanf and extras and all of that stuff is buried safely inside this process function. And when I'm working with my main program and I'm adding debugs and stuff, I don't have to work through, you know, scanf and fgets and all this other stuff. Most of that's buried inside here. So it's just input, process, prompt, input, process, prompt. All right, process is all the stuff that we did in 224. We talked about in the beginning of this project. So I switch on the first character. If it's an I, do your whole scanf to see if it's I followed by an int. And if it is, then we're going to insert, see if it's already in the list. If it is, print that message. Otherwise, go ahead and call your add function and say success. If it started with an I, but it wasn't, you know, I followed by exactly an integer, I print out this usage message. So usage is just this function that will print out, you know, a list of legal commands. And so each of these commands is like this. P is just a print, S is just a search, followed by an integer, D is a D followed by an integer, and X kicks you out. And when I do X, I return a 0, which is the flag saying, hey, the main loop should exit. If the input doesn't match any of these, then it calls the usage function to print out a help message, and at the end of all this we return a 1 which says keep going, and then the usage message is just, you know, the prints for help. So functions is the workhorse, right? And so you know, here's some examples of how you might document the functions, right? I have a function called init. It returns a pointer to a my node. Takes no arguments, returns the address of the sentinel node of a new empty linked list. Data field is populated with magic number as a flag to help us notice if we accidentally process the sentinel as a regular node. If init malloc fails, this function will return null. There's nothing in here to stop you from, you know, running out of memory and returning null. But if you do that, and your main program tries to use what it thinks is a sentinel node, your main program will segfault. Right? Well, that's a good thing to know if you're planning to use this init function. You might get back an invalid sentinel node pointer. So that's what that's mentioning. And the actual init function, right, just do your malloc, set the next node to null, set the data to your magic value, and then return that sentinel node's address. And so, you know, my function is 4 lines and my comments are however many lines. Here's the add function. Insert a node into the linked list. Takes a pointer to the sentinel node, takes the integer to add. Integer is added so the list remains sorted. What does sorted mean? Smallest next to the sentinel, largest at the other end. And then I put a note in here. This will insert duplicates if asked to. So if you don't want duplicates, you probably want to do something like call search before you call add. And then it returns 1 if it's successful, 0 if it fails, meaning it's out of memory. And the code, you know, we worked through in multiple sessions. But, you know, previous is the node before the one I'm interested in. Current is the one I'm interested in. Up in the beginning, I go ahead and make a new node once, check to see if we're out of memory, save the data field. And then here's the main loop that looks for the right place to insert. So if the current node comes after the number we're inserting, have the previous node point to the new one, have the new one point to the node after it, and return success. Otherwise, we didn't do an insert here, we have to check the next node, so move down the list. And then if we come out of our while loop, we are at the end of the list, and we should insert after previous. So current is null, previous is the last node, so we have previous point to our new node is the end of the list. Print, not a lot of problems there for people. Start with a node after the sentinel, just keep printing till you try to print null and stop right before that. And not a whole lot of documentation in there. It might be nice to know how this data is going to be printed. It's printed with a %D. So it should be just, a small integer. It comes out in a single line with a space between each number. Delete, similar to add, and we've already gone through this code. And again, first argument is this, second argument is this, return value is this, and then some comments. If a data value appears more than once, only the first occurrence is removed. And this function does not rely on the list being sorted. If we wanted to rely on the list being sorted, we could speed this up, right? We could search until we find a number that's smaller than the number we're trying to delete, and at that point we could say, hey, your number's not in the list, because we know the list is sorted. But I didn't bother doing that, and that wasn't a requirement. Same thing with search, right? Does not rely on the list being sorted. We could get some speed up, but it would still be order n, even if we stopped when we knew we were past where the number would be. And then cleanup. Most people were managed to delete all of the nodes from their list and free up their memory, which was great. It's a tricky thing to do. So cleanup just releases all the memory associated with it, and just put a little note in here that after you do this, the sentinel will be null. Well, it won't be null, but it will point to a memory location that's no longer the sentinel. And so if I free my list, if I call cleanup, and then I try to do something with my sentinel, it's unpredictable what's going to happen. It will point somewhere in heap memory, but it's probably not going to be a sentinel node anymore. That memory could be reused by something else at that point. So after calling this function, any further attempts to use it will result in unpredictable behavior. And then this was... Go ahead.
If someone was building a main function that uses the cleanup and the init function, you would just have to basically specify to use the init function before or after the clean function, right? To reinitialize a new linked list.
Yeah, if you call cleanup and you want a new linked list, you would have to call init again, exactly.
Okay.
And the way that you wrote PA1, whether you realize it or not, you could have multiple linked lists at one time. I could have list 1 equals init, list 2 equals init, list 3 equals init, and then I could add to list 1, I could add something else to list 3, I could delete from list 2, and these are independent linked lists, right? Which is kind of nice.
Almost like it was an object.
Yeah, almost like an object, right? So so this was a piece of test code that I used. So this is called my main. I link this in with your functions.c. And it just calls your init. It adds a handful of things, prints it out, what the list looks like, and then searches for some things that are in the list, and it should, return a 1. Searches for some things not in the list, it should return 0. Searches for the sentinel, should return 0. Tries to delete 3 nodes, that should succeed. Tries to delete 4 non-existence nodes, those should all fail. And it should leave me with a list that's 10, 30, and 40. And then I call cleanup. And so I can just val grind my main and look at the output, and the output should be exactly what I'm expecting, because it's my code, it's my format, and so on. But it's exercising your code. And when you're developing code yourself, right, it's nice to have some test beds sometimes. Instead of just running main and saying I space 10 enter, I space 20 enter, right? You have this whole package of functions. You can make your own test programs that just call those functions and exercise them. You could add 1,000 nodes and delete those 1,000 nodes, and then print out your list and make sure it's empty. And it's your code, and how these functions are set up, and so you always have the option of exercising it a lot of different ways. The other thing is, I don't want you sharing your main.c or your functions.c with other people, but if you were to write your own test bed like my main.c, right, you could share this with somebody else, and they could link this with their functions.c and see if it works. And coming up with things to test, cases to try, that's totally fair game for collaborating with other people. I'm okay with that. All right, so let's see. My code is a little more verbose than it needed to be, and I probably should have stopped and thought a little more critically here. It worked, however. Um, so, yeah, it's definitely fine to err on the side of being more verbose. I think especially in school, and especially if you're trying to learn something like linked lists, right, where there's weird stuff going on with pointers and mallocing memory. I think it's helpful to be more wordy rather than less. And I'm always writing tons of comments in code, and I'm writing them just for myself. And it's just stuff to help me go back. And sometimes I'm writing comments because I don't feel like writing code. I'm like stuck and I haven't figured out how to get through some mental log jam, and so I'll just start making ASCII art, and do that until I figure out what I actually want to do code wise. So verbose is okay, I think. All right, so PA1 is graded. Comments are posted. Definitely, if you had problems with the linked list functions and such, come by office hours, and let's work through it. I think pretty much everybody was very close. If they didn't get everything to work perfectly, it looked like people were definitely on the right track. And it's just sort of some details. Also, a number of cases where the code looked far more complex than what we've been talking about in class. And I'm thinking it's because either someone didn't understand or didn't notice when we talked about algorithms in class, and then just sat down and tried to figure out from scratch, well, how would I insert a node, or how do I move down the list? So definitely come by and we can talk and go through what you did and figure out details like that. Also, just for reference, fewer than half of the class turned the assignment in on time, so more than half the class used at least one slip day on this. And that's okay, if it caught you by surprise or something, but there's 5 assignments, and the other assignments are probably going to be longer than PA1. PA1 is the hardest in the sense that, it's the kind of first one where we're digging into using mallocs and pointers to structures, and a lot of the machinery, the mechanics of that is new to us perhaps. But the amount of detail and the number of moving pieces in future assignments will probably increase throughout. If I had to do this again, I would really split up my add function rather than try to force it into one big complex function. Yeah, that would be cool. And I saw some people do that, and that's totally fine, right? As long as your function prototype for add is the way it's specified. Within add, you could call a locate function, and you could call something else, and so on, and that's all good design decisions you can make. Yeah, question, comment? All right. Any other thoughts or comments on PA1?
I would really have split up my add function there if I had to do this again. Instead of making it one big complex function. I probably could have saved some code in other functions too if I did that too.
Right. Yeah, and that's a good design decision you can make. All right, so I'm gonna say let's take a break. A few minutes early here, and get PA1 out of our brains, and then let's come back and rehash stacks really quickly, and then talk about queues. And then Thursday, I think we're gonna go on. We're gonna talk about hashes, and that'll be good stuff. So let's do a break, and let's come back at 14:03, so 5-minute break. I'll be back. Need a way to mute my microphone.
Do you not have that?
No. I mean, I can pull the plug, but then poor operating system is like, ah, where'd my microphone go? I can see you off camera. Thank you for the cappuccino.
You're
It's really good. Best piece of your desk.
doesn't surprise me.
You want it for like Mara's collection of stuff?
No, please. I'm out of categories for that.
You'd be Kaya's best pieces.
No.
DHL pinged a while ago. They say they're delivering this afternoon.
Oh, cool.
They're crazy. It's both shipments, I believe.
Oh.
Yeah.
I ordered more boxes.
What kind of boxes?
The same ones through Instacart again.
The plastic ones? Oh no, through Fred Meyer's?
Mm-hmm.
Oh no.
They're coming tomorrow.
Okay.
If they have them.
Cool.
Because they're way more expensive on Amazon and everywhere else, so we'll see what happens.
And the Coca-Cola.
And we'll carry the shame again.
Yes. All right, welcome back. I had some printed circuit boards designed them last week, and sent the shipment into 2 companies in China, and it's supposed to be, you know, like 10 days to show up, and they finished building the boards in about 3 days. They sent them, I don't know, like 3 days ago, and they got to Hong Kong, they got to LA this morning, and they're actually on their way to my door, like right now, which is like unbelievable. I mean, this is like halfway across the world in like 2 or 3 days, and super inexpensive shipping too. It's a very
It'd be super exciting if, like, the prevalence of 3D printers could transfer over to, like, the prevalence of printing your own circuit boards.
Oh, it's getting there. There's people who have made homebrew circuit boards with 3D printers, and yeah, it's definitely it's getting to be a thing. And I hope / think that 3D printing is going to help change a lot of things down the road. Because you can print a lot of stuff, and the 3D technology gets better and better all the time. And you can print with proteins and things like that too. So yeah, it's a fun time to be an engineer. All right, so quick rehash of stacks. So what's the number one thing that you would tell someone about a stack? Someone's like, what do you think is the most profound thing about stacks? What would you say?
First in, first out. Yeah. First in, last out.
First in, last out. That's probably what I was thinking of. This idea that, you know, you can add things into here, and when you want to remove, you remove the last thing that you put in. And so last in, first out is stack based. And so you can implement this with a linked list by just, you know, put stuff in the beginning and remove stuff from the beginning. You could also put stuff at the end and remove stuff from the end, but that's a lot less efficient, because to add to the end of a list, you have to move all the way down the list to get to the end and then put your node there. And to remove, same thing. So putting it in the beginning right after the sentinel, order 1 operation, right? And we talked about how you could implement this using arrays. And the idea is, you know, you have your array, which is a fixed set of locations. And then we have something like a stack pointer, which tells you maybe where to do your next push or where to do your next pop. And this is a little different from a stack of books, right? When you stack books on a desk, the place where you put the next book is physically different from where you put the first book, right? It's moving up in the desk, or it's moving back down. But there's other kinds of stacks where the top physically stays put and the whole collection of things moves down or moves up. For example, if you go to a buffet and they have, you know, a thing of plates in the beginning, you take a plate off the top. That's like, you know, some container like this. It's usually sitting on wheels or something, and it's got, you know, some kind of spring-loaded platform here, and you stack your dishes on here. And if you take a dish off the top, that's a pop operation, the spring expands a little bit and all of these plates move up, and now this plate moves up to the top. And so this also has the structure of a stack, right? A last in, first out. But you always see, you know, the thing that's on the top of the stack at the same spot. It's right here at the very top of this appliance, right? And when you want to put something on the stack, you put it in the same spot right here on the top of the appliance, and everything moves down. In a computer, right, it's inefficient to try to move a bunch of things in memory. And so instead of moving things down, instead of storing our first thing here and then to push something else moving everything down and storing the next thing here, we change where we consider the top of the stack to be. So that's what the stack pointer does for us. And it, you know, if we push an A, it'll go here, and our stack pointer will become 1. If we say push again, it'll store at index 1, and we'll change this to 2. If we say push again, we'll store at index 2, and this will change to 3, and so on. And just be aware that there's sort of a fundamental different feel between that and, say, what we're doing with a linked list, where we're always inserting right after the sentinel, right? In that case, the top of the stack's always, you know, the thing the sentinel points to. And we're kind of, you know, moving these things down in the sense that we're shoving a new thing in front of the stuff that was already on the stack.
Wouldn't there be any way to avoid moving that memory around? Like, let's say you had a stack or a queue. It always goes one position after the last one.
Mm-hmm.
So you don't have to move everything around. You can just walk the memory still.
And that's basically what happens when we use a stack pointer with like an array. Is that if we wanted to, if this is our stack right now and we want to push a D, instead of putting it here and moving everything down, we'll just say, oh, we'll just add it right down here. We'll leave these things where they are, but instead of having this be the top of the stack, we'll say that's the top of the stack. And so we're just kind of looking at it differently, and that saves us moving things around in memory. And with a linked list, the same thing happens, because the whole idea of a linked list, remember, was we could insert something like in between here and here without having to move these things. We could simply make a new node, point to that, and it effectively goes in the front. Is there a time penalty for jumping to non-consecutive memory addresses as in a linked list? That is a deep question. And the answer is perhaps. And we're still kind of in this mode where, you know, we're going to finish talking about queues today, and the A section we've just begun. So we're still, you know, a class ahead of the other sections. So small diversions are fine. So I'm going to take a small diversion right here and mention cache memory. And if you've done Engineering 270 with me, we probably talked about cache memory. A lot of what makes computers fast is the validity of this assumption that we access data near other data that we access. There's a locality in space to the way we access memory. And architectures take advantage of that. CPU hardware, memory management systems take advantage of that. And so theoretically, if we have a linked list that's scattered across wide areas of memory, it could be very inefficient to access that. Whereas accessing something in a consecutive array could be extremely fast. This actually,
With that.
yeah.
So I know with like a hard drive disk, you know, that could be a big deal. But does the implementation of SSDs, does that help at all, time-wise? Because now you're not looking for the data; you're just going straight to it.
Well, it helps, but going to it is still an issue. So this is 11 inches from one side to the other. So, you know, from here out to about here, right, is about a foot. That's a nanosecond. Okay, that's how far an electron can go in a billionth of a second. So 3 inches, that's a quarter of a nanosecond. That's 250 picoseconds. That's about 4 gigahertz. So if you were to try to run a CPU at 4 gigahertz, each clock cycle your electrons could travel 3 inches. So think of a motherboard, and think of a cable coming out of your motherboard going to your SSD, and think of the physical dimensions of the solid state drive. And if you've got a 4 gigahertz CPU, from one instruction cycle to the next, your electrons can only travel 3 inches. if they're moving at the speed of light. In fact, drift speed is slower. So it's going to take a lot of clock cycles just to wait for the time it takes an electron to leave the CPU, go through all of the circuit traces on the motherboard, get to the connector where the SD cable is plugged in, go down that cable, get to the SD card, come back, right? That's not even counting access time. So basically, as soon as you leave the CPU, your performance bottoms out. Additionally,
the M2 slots are a lot faster than
I think that's why they're a lot faster, yeah, because they're
like right next to the processor.
yep, they're physically closer, and they may be lower voltage, and the voltages inside CPU are very small, and the currents involved are very small. To push a signal through a wire or a circuit board trace, you need more current, and it takes time to generate the power needed to push those electrons out, and that's a delay. And there's all these details that if you get down to doing like integrated circuit design, you start seeing, how do you take a one coming out of a transistor in silicon and use that to raise the pin on a chip to 5 volts or 1.8 volts or whatever your logic level 1 is. And it's a lot of cycles. So yeah, if you can keep stuff on the chip, that's close. So most chips for CPUs have caches built in. And there's a level 1 cache that's very, very fast and very small, and usually an L2 cache that's a little slower and a lot bigger. And then sometimes an L3 cache, which is even slower but much bigger. And those may all be, inside the chip itself, so that everything can happen without leaving that substrate.
And those are usually static RAM, usually?
Those are usually static RAM, which means they're frightfully expensive, because static RAM is really expensive compared to dynamic RAM, which is just a bunch of capacitors. It's also physically larger. It takes several transistors to store 1 bit, whereas dynamic RAM, it takes basically 1. So we don't like using a lot of static RAM. You're not going to see a machine with 16 gigabytes of static RAM on it. But it is faster than dynamic RAM. It's also a lot more power involved in storing things in static RAM. And yeah, so that reflects the current trend of faster and faster processors putting large amounts of L3 on the CPUs. So yeah, and jumping around memory locations, the other place it'll come up sometimes is this: if you have a 2-dimensional array. So you've got, say, 1,000,000 by 1,000,000 numbers stored in memory. Let's say these are doubles, because you're doing some kind of matrix operation, right? We like 215, and depending on your compiler and what language you're writing in, right? The elements in this array may be stored, in this order. This would be stored in memory 1st, 2nd, 3rd, 4th, 5th, 6th, what we call row major, or they could be stored, 1st, 2nd, 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, in column major. Which means if you have a pair of nested for loops for I equals 1 to 1,000,000, for j equals 1 to 1,000,000, and you go through and you do something with each element from your array, the order of those loops, the I and the j, can critically change the speed of your program. Because if my data is stored sequentially in this direction, and I happen to write my for I equals for j equals loops so that I access data in this direction, well, each time I make a data access, it's going to be, 8 million bytes from the previous location. And my cache is not going to work, right? I'm just going to be peppering my memory with these locations that are very distant from each other, and my performance will totally bottom out. And that's just, from saying for I for j instead of for j for I. And that's purely, from the notion of program correctness, it looks like either one is fine. But from performance perspective, right, very, very different experiences. And that's something that, if you've done Engineering 270 and you've done a computer architecture class and you know something about compilers and memory structure, right, you might realize this and find a way to write your code much more efficiently. So all this stuff is good. All this stuff comes into play, and very little of what you learn is completely useless in school. It's just not always clear what use it is at the time.
So it sounds like as far as we're concerned, we don't need to take that into consideration at all for linked lists.
No, it's not. It's not a practical problem for linked lists. But if your linked lists were, containing a billion nodes, it might start to be an issue. But you don't usually do linked lists with a billion nodes. You would probably go on to like a tree or some other kind of data structure. All right, so let's talk about queues. So queues are similar to stacks, except they have a FIFO structure. So it's first in, first out. And so the physical model you can think about for queues is basically just a line, right, or a queue, as you call it in some parts of the world. So here's a line, and let's say we're at Fred Meyer, right? So here's the cashier. And customers enter this part of the line and they move through, and when they get to the cashier, which is the head of the queue, they get their groceries rung up, they pay for their groceries, and they can leave. And while somebody at the head of the queue is being processed, right, multiple people can come in the back of the queue, what we call the tail, and they can queue up behind the person in front. And so let's say, person A comes into the queue. Well, they go to the head of the line, the head of the queue, and person B comes in, and person C comes in. All right, they're sitting in the queue, A, B, C. And the cashier is ringing up the groceries for customer A. They're being processed. And customers B and C are waiting. At some point, customer A will leave the queue. Who's going to be the next customer to be processed? It's going to be B. And it does not matter how many more people come in the back of the queue. Guaranteed, once A is done, B is going to be the next one. So the first customer in line is the first customer out of the line. The second customer in line is the second customer out of the line. And this is very different from a stack. In a stack, right, if you have a stack of books, you keep piling them up, you keep reading from the top. Those ones on the bottom, you may never get to those. Right? Because you're going to keep getting new books and putting them on top and reading those before that first book you put on the table. With a FIFO, you would, pile your books up, but you'd always take a new book from the bottom of the pile. So that the first book you put on the desk, that's the first one you read. And the second book is the second one, and so on. So we could take A out of the queue, and now B is being processed. We could take B out of the queue, and now C is being processed. And maybe D, E, F, G come into the queue. And we take C out, and now we put in H and I, right? But D is still at the head of the queue. When we're done with D, we take them out, and now we're going to process E. So you can think of a line in a store if you want, and it's a first in, first out structure.
It's kind of like an algorithm, just executing from top to bottom.
Yeah, and this is actually tied into how a lot of things work in operating systems, right? This is how jobs get scheduled. If you're currently running job A and jobs B and C get queued up for execution while they're sitting behind job A. And when job A, finishes its slice of execution, job B will get a shot at the CPU. And when that's done, job C will get a shot. And if A's not done, when it comes out of being executed, it'll go in the back of the queue. And so you can describe scheduling algorithms in operating systems using queues.
This is how installers and stuff works. If you're already downloading and installing a game,
yeah,
the next one's queued up behind it.
Exactly, yeah. And all things being equal, right? If I queue up 5 more downloads, the first one I queued is going to run next, and the last one that I queued is going to run last. So it's last in, last out also. But there's also the notion of priority queues, right? There's might be a way to say, hey, download this one, before the others, and then even though this was the last one that I marked for download, I might be able to say, hey, this should be the next one that you download. So we could have multiple queues, each with a different priority on them. That's something else we find in operating systems, because system critical process will run before my C program runs, because it's got a higher priority.
Oh, so you're saying, so like if the operating system has a install and that's a higher priority, then your game that's going to prioritize the operating system install.
Yeah, so if
Driver or whatever.
if you look at a top command, right? So there's a priority for each job. Priority 20 is very low. Priority minus 51 is extremely high. And so all things being equal, right? A job with a higher run priority is going to run ahead of a job with a lower one. And scheduling those and figuring out the structures for them is fun stuff. It's an interesting area.
So the user might not see that kind of stuff, but that's what the operating system's handling.
Right. And when you're trying to compile a program and you type GCC and hit enter and the characters are coming out really slowly and it kind of sits there and stares at you, what's happening is something else on the system is probably taking precedence. Or there's just so many people that you're taking turns, but you're taking turns with 20 other people. But there's a good chance something higher priority is happening, and it's getting more than its fair share of the CPU. So let's look at queues as an abstract data type. So remember this idea that we can look at a data structure in terms of how do we use it, and we can look at it in terms of how do we implement it. So the abstract data type view is how we use it. What is an abstract queue? Forget about a queue made with a linked list, or a queue made with an array, or a queue made with magic fairy dust, right? Let's just think about a queue. What is a queue? What does it mean? So this is an abstract data type view of a queue. And so we probably have some kind of initialization routine to do whatever has to be done to make it possible to use a queue. We have an add routine, which says I want to put something in the queue. And we add to the tail. So the two ends of the queue are the head and the tail. And this is mostly standardized, but occasionally you'll find something that uses the opposite convention. But most often, and every time we talk about this in this course, when we say add, we're going to add to the tail. We can also remove. And when we remove from the head. Right, so think of head of the queue as the point where something leaves, and the tail is where you go in. Back of the line, front of the line, basically. So we certainly want to be able to add something, remove something, and what makes the queue is the fact that this follows a FIFO kind of behavior. So the first thing you add will be the first thing you remove. And then maybe you also want to know, is the queue empty? Or maybe your remove function can just indicate something to you in its return value saying that it's empty. But you might have a separate function which says, is it empty? And you might also want to know, is it full? Is there space to add something more to the queue? And then you might want something like, I don't know, maybe a flush, which says, empty out the queue. Just get rid of everything that's in there. I'm closing my line. And there could be other functions in there. Maybe you want something which says how many things are in the queue, and so on. But at the very least, right, we need to initialize, add, and remove. Those are the two main essential functions to a queue. Add something to the tail, remove something from the head. And so if we were to write a queue package, which I have a feeling you're going to do for PA2, which I'm going to write up later tonight, if you were to make a queue package, right, you would need to create functions to do these things. the implementation of those functions, right, is independent of the fact that these are the functions, these are what they do, and so on. But as an abstract data type, we just kind of think of, here's the interface to our queue. And if we wrote a main program to add things to queues, remove them from queues, we would just call these functions. And we wouldn't really be concerned with what are those functions, how are those functions doing what they do. We're concerned with this will add an element to the tail of the queue. Is there a linked list? Is there an array? I don't know, I don't care. So that's the abstract view of a queue.
Seems like you would use it for jobs.
Yeah, definitely. There's queues used for job schedulers in most operating systems.
Would it be just like a queue of function pointers or something like that?
Well, so your queue could have, could have letters, could have customers, could have integers, could be pointers to some kind of data structure, which is what they would be for an operating system. Maybe not a function pointer directly, but a pointer to what we would call a process. And so somewhere in the operating system, there's a big array of pointers to processes, and each process is, a copy of the memory for the program, a copy of the code, a copy of the program counter where it was at when it stopped executing, all the values of all the registers, all the information about the process that was running, right? When the process stops running, all that information gets saved somewhere in memory. And you can access that through, some kind of pointer to a structure. So you might have a queue of those process pointers. And when it's time to process a new job, you take the current job, put it in the back of the queue, take the job at the head, and you use the pointer associated with this thing to find that job's information. Grab all of its instructions, load those into memory. Grab all the saved values of the registers, load those into the registers. Look at the saved program counter, put that in the program counter, and now the code runs. And meanwhile, you've set a timer so that after, 1 millisecond, an interrupt occurs, and part of the interrupt will be, okay, let's stop that job, let's find a new process that wants to run, and so on and so forth.
Presumably there'd be a couple queues for depending on the priority of the job. And
Yeah.
maybe if the job's almost done, it might have a way to check and see and maybe just finish it up really quick. Maybe.
Mm-hmm. Yeah, there's a whole science to job scheduling, and you can do a very straight round robin where everybody just gets a fixed amount of time regardless. You could do something based on how much work the job has done. If it's very CPU bound, maybe you give it a little more time. If it's doing one little bit of work and then waiting for I/O, maybe it becomes lower priority, and so on. And that's all fun magic to figure out in like an operating system design course. And the more courses,
Use it.
go ahead.
Go ahead. I'd say you might use it for event-driven code.
Yeah, definitely.
I guess you still might, right?
So 223 will talk about event-driven code in Java, but yeah, most code that we write, most modern code is event-based. We don't sit in a loop and keep doing something. We basically wait for something of interest to happen. Hey, somebody clicked the mouse. Hey, a packet arrived from the network adapter. And you could have a list of all the processes that are interested in mouse clicks, sitting in a queue. You might have another queue of events, and while you're processing the mouse click, if a keyboard stroke appears, right, maybe that gets pushed in the queue. Basically, anytime you need to remember a bunch of stuff, deal with them one at a time, but you want to deal with them in the same order in which they occur, you're probably going to use a queue. So, processing keystrokes, well, you want to do those in order. If you do that with a stack, everything you type would come out backwards, which would be fun.
I spent some time over break writing this Echo server in C#,
Mm-hmm.
and I had to use delegates every time some data came down the line. So I was using like asynchronous receives. But I can imagine if you needed lots and lots of events to happen. There are lots and lots of things to happen when an event gets triggered.
Mm-hmm.
This would be super useful.
Oh yeah, definitely. I've been working on an event-driven package for the past couple of weeks, so this is all like close to my brain right now. So that's why I'm kind of going off on it. All right, let's look at implementations. So again, this is how do we write an add function or a remove function or things like that. And the first and probably most straightforward to code approach is to use a linked list. So this is going to look a lot like what we did with stacks. Imagine we have, our Sentinel node. And, maybe this is a queue. And one end is going to be the head, and the other end is going to be the tail. And whichever end the head is, when we want to remove something from the queue, we're going to pull that thing out and then remove it from the list. And when we want to add something to the tail, we're just going to insert it into the list at that point. And so I'm going to set up my head to be right next to the Sentinel. And I'm going to put my tail at the far end. And so add some number n. Let's just do a queue of numbers here, because that's what we always end up falling down to. It's just a queue of numbers. So we're going to add n to our list. So we want to add it to the tail. Well, we have to get to the end of the list, and we know we can do that by start at the Sentinel and just move down until our current node's next pointer is null. And when that happens, we know this is the last thing in the list. So we make a new node with n, we change this thing's next node to point to that new node, and we're done. And then to remove, well, that's like a pop command for our stack. We basically look at the value that the Sentinel points to, whatever the data field is there, that's the number we're going to remove. And we change the Sentinel to point wherever this first node is pointing, and we free this first node. And that's really all there is to it. Initialization is the same as initializing a linked list. We just make a Sentinel node, have it point to null. And if we wanted to see if the list was empty, we just see if the Sentinel's pointing to null. And if it is, we know there's nothing in the queue. We can't effectively tell if the queue is full, because in this case, full means, out of memory. And that's a hard thing to do. That's a peculiar case. And if we wanted to flush this, right, we could do our cleanup routine, but keep the Sentinel intact, but basically just start from here and release all of these nodes from memory and change the Sentinel to point to null. So each of these functions is 2 or 3 lines, except for add. Add is a little tricky because we have to move all the way down to the end of the list. And that's not only a bit of code, but it's also order n. If we had 1,000,000 things in our queue, we would have to do 1,000,000 iterations of our loop to move down and find the last node. But any ideas how we could speed that up?
We could have some sort of variable to know like how long the list is, and walk precisely to the right spot. I guess it doesn't really stop you from being ON, but maybe it saved you some time if it wasn't at the end.
So we can do that. We could have a variable called tail pointer, and always have tail pointer point to the last thing on the list. And so Sentinel points to the first node, points to the Sentinel. But we have a separate my node pointer called tail pointer that's always set to the address of the last node in the list. Yeah?
What if we had a pointer to the front, the tail, and the middle? And then if we knew the length, we could go from the middle and work our way upward if it's above the middle, or work our way downward if it is between the head and the middle.
Yeah, that's going to be a binary tree. And that's exactly what we're going to do. So hold that thought, and you'll see something glorious in another week or 2 weeks maybe. Because we're going to do that, and we're going to do it in a way so that after we've gone to the middle and we've decided to look at the upper half, we can go to the middle of that subsection, and we can keep doing that. And that's exactly how we're going to develop a binary tree. And it's going to give us that high-low ability to search this linked list in order log n instead of n. And then we've got a really good data structure.
Nice.
Yeah. All right, so for a queue, we're going to have a tail pointer that always points to the last element in the list. And so now our add function is a fair bit simpler. So, new equals malloc, the usual stuff. New data equals n. New next equals null. So we've got a new node. There's new. And now we don't have to walk the list. We know the tail pointer is the current last node. So we could say tail pointer arrow next equals new. Tail pointer is the address of this last node. Tail pointer arrow next says follow that address to the actual node, take the next field, set that equal to new. That puts this in place. And then all we have to do is say tail pointer equals new. And we save this in an evil global, right? So that next time it's still got the same value. And now tail pointer is pointing over here. And we're all set for the next time we add. So it's a fixed number of steps to add to the tail of the queue, regardless of how big the queue is. And that gets us back to order 1. Order 1 means precisely that. It means even if we have a million things in here, it's the same set of operations, the same number of operations to add a new node. And then removing, since we remove from the head, that's just going to be, 3 or 4 operations, regardless of how big the array is, how big the list is. And this trick only works if we have the tail out here and the head at the beginning. If we try to switch them around, we can't do the tail pointer trick. Because if we try to remove from the end of the list, we need to back up, and we would need our tail pointer to point to the thing before the last node. And once we remove the last node, we need to back the tail pointer up somehow, and there's no easy way to do that. Unless we have a doubly linked list, which is another topic. But like this, head in the beginning, tail at the end, this works great. So questions about this?
I know where you're going with the firewall thing and what should be available when somebody's using your code versus when the code is actually operating. So, without skipping too far ahead here, is there any way in C to declare private?
I don't, top of my head, I don't think so. I'm thinking there's probably ways you can fake that, but effectively, no.
Okay.
I mean, a function that's callable is callable. I mean, you can do some hiding of information, but just the way that you have to pass things around. I mean, if I'm calling my add function from PA1, I've got to pass the linked list, the pointer to the struct node, to the add function. And so I have, the location of the sentinel node in memory, and I can monkey with it. And there's really no way to sort of prevent that. So
there's
whereas Java, you know, you can make fields private and methods private and all that good sort of stuff.
no encapsulation, huh?
Yeah, yeah. No, that's the whole point of objects, right? Encapsulation and
Yeah.
information hiding. So we'll get there, and it'll be fun. But for those who haven't done object-oriented stuff, right, working through um, data structures like this, right, is critical to understanding, you know, what's actually going on with these structures. But doing it in C, you know, which lets us get down to the lowest levels, requires us to do some kind of ugly things that will look ugly in retrospect. When we get to 223, where we have an object-oriented language, namely Java, we'll find much more elegant ways to do the things we've been doing here. And it'll be worth the wait, I believe.
If I may, why do we use Java rather than C++? Because it seems like C++ is a more natural outgrowth of C. It's like an extension of C, kind of.
It is, but it doesn't seem to have the same popularity as Java. It doesn't always feel as consistent as Java.
Really, really, really verbose.
Yeah, and I mean it's got nice things like operator overloading and stuff like that. But Java is what WSU uses, and a lot of other schools use, and so that's what we target. But you know, if you know C++, you can switch to Java pretty easily, and vice versa, as well. So it's mainly just finding, you know, some object-oriented system to dig our teeth into.
That makes sense.
Well, just like with stacks, we can also implement queues using arrays, and this is, you know, quicker and dirtier, because you can make an array just by saying, you know, integer array bracket 1,000, and you don't have to deal with all the linked list stuff, right? And it can be just as fast, but it can't grow without bounds. When we make a stack using an array, we decide ahead of time how much stuff can we store in here. And that has the disadvantage of, one, you know, only being able to hold, say, you know, 10,000 elements, and two, using up 10,000 elements in memory whether we need them or not, right? We're chunking off a set of memory locations and saying, you know, here's our stack. Same thing with a queue. But the implementation with a queue is so quick and easy that sometimes we'll prefer this to a linked list. So what does this look like? Let's make an array, and let's just imagine an array of 8 locations. And this is going to be our queue. And in the case of a stack, we have a stack pointer, which we can say this is where we're going to put in the next push, or we're going to pull the next pop, or something like that. In the case of a queue, we need 2 of these pointers. We need to know where the tail is and where the head is. And so we might, you know, have a head at 0 and also have a tail at 0. Okay, so H that's the head. That's where we remove. And tail is where we add. And the way someone suggested to remember these, that's what I've been using, is they're anatomically backwards, right? You put food in at the head, take it out the tail. Head is where we remove the items from. Tail is where we put the items into. And so 2 pointers. And when you want to add, what do? We say q bracket head equals n. So we put our data here, and then we increment the head. So at the next time, right, so if we add an A to our queue, A will go right there, and our head location will change here. If we add a B, B will go right here, and our head will change here. If we add a C, it'll go right there, and our head will change here. So if we've added A, B, and C, there's 3 entries in our queue. And the next entry we add would go right here at the 4th element. But if we try to remove, we're going to remove from the tail. I just did this backwards. Alright, new picture. I guess there is no good way to remember this. You just have to write it down. Alright, so tail is going to be where we add, and head is going to be where we remove. Right, which was what I wrote down, but then I didn't use that. So let me write it like this. Alright, so let's add an A, and so we'll put an A right here, and we'll move the tail to point to element 1. We'll add a B, we'll move the tail to point to element 2. We'll add a C, we'll point the tail to point to element 3. Alright, so this is where we're going to add the new entry to the queue. But if we now say, you know, let's remove the first thing from the queue, we're going to use the head pointer, H, and say, okay, we should remove element A. So we'll give A to the user, and we'll move our head to point to the next location. So our add function looks like Q bracket tail equals N, and then increment the tail. Our remove would be return Q bracket head plus plus. So use the head pointer to find the thing that we're going to return and then increment the head. So if we say remove again, we'll pull out the B and we'll change the head to here. If we say remove again, we'll pull out the C and we'll change the head to be here. Alright, so here again, the stuff is not moving around in the array. We're changing what we consider to be the head and the tail of the array. This works great, except that, you know, eventually we're going to hit the end of the array. So let's add a D and an E and an F and a G, and our tail is now pointing right here. This is where we're going to add the next thing. And the head of the queue is right here. D is going to be the next thing we remove. The next thing we add is going to go at location 7. Well, let's say we add an H. So we're going to put an H in here. What should we do with the tail pointer? We could increment it and have it point to location 8, but if there is no location 8, that's going to be a problem next time I try to add something. But in fact, all of this is unused right now. Yeah, there's an A, B, and a C, but I've already removed them from the queue. So after my queue was 7, if I add something else, instead of incrementing to 8, I'm going to set my tail pointer back to 0. And now if I add something else, I'm going to put it in at location 0, which would be I, and I'll move my tail pointer to here. And now if I start removing, I'll remove the D, the E, the F, the G, the H, and my head pointer is pointing right here. After I remove the H, instead of having my head pointer go to an 8, I'll roll it over and go back to 0. And now the next time I remove something, it's going to be an I. So this is a circular queue or a circular buffer. And you can think of it as an array that looks like this.
Seems more like just a loop you can keep adding to.
Yeah. So it's an array that we think of as, you know, the element after index element 7 is index element 0. And so if I put something in here, I'll move my tail pointer. If I put something there, I'll move my tail pointer, and so on. And if I'm removing, right, I'll move my head pointer and take off. Well, if my tail pointer happens to be pointing here, and I want to store something, I'll store it in here, and I'll just change my tail pointer to be right here. And as long as I don't step on things that are actually in the queue, this works great. So that's the effect of a circular queue, which is how we implement a queue with an array. We have 2 pointers, head and tail, and we have this rollover behavior, right? We're always incrementing our head and tail pointers. Every time that we add or remove, we're going to increment those pointers to a higher index. But if they reach the end of the array, instead of falling off the edge of the earth, we just send them back to the beginning. And we do that, you know, as long as we have space. And so the actual location of the elements in our array, originally it might be, you know, if we push 3 things, it'll be these 3 elements that contain our data. But after we've done some removing and we've put some things back on, we might find, you know, that these 3 elements contain the 3 elements of the array. Or maybe these 3. Right? So the kind of active section between the head and the tail is moving around here. And so we don't have to move things in memory. We don't have to, you know, get down here and say, oh, we're out of space, but we got empty space here. Let's shove everything up in the array. Right? The data never moves, just the pointers to it. And so now our add and remove functions get a little more complex, but really not bad. So add n, so q bracket tail plus plus equals n. If the tail is equal to 8, set the tail equal to 0. Assuming that, you know, our array held 8 things, but whatever the length of it is. And then remove, so return value equals q bracket head. Increment the head, and if it's equal to 8, roll it back over to 0, and then return this return value that we saved. So there's your add function, there's your remove function. Is empty and is full get interesting. So is empty is straightforward. Anytime that the head and tail are equal to each other, the queue is empty. All right. So when we begin, right, a knit, the initialization routine is just set the head and tail equal to 0. Or in fact to any value. As long as they're equal to each other, the queue is empty. Telling when the queue is full is a little trickier. And this is just one sort of edge case to keep in mind. So let's suppose our head and our tail are 0, and we add a bunch of things. We add 7 things into our queue. So our tail pointer is out here. Our head is still at index 0, our tail is equal to 7. And there's still one spot left in our array, right? We could still store something in this 8th location. But if we say, you know, add one more thing, let's add an h, well, we're going to add an h here, we're going to increment the tail to be h. H is too big, it's going to roll back over to 0, the tail is going to go back to location 0. And that situation is indistinguishable from when the queue is empty. In other words, if the queue is completely full, exactly every element has something in it, the head and tail will be equal. And if the queue is completely empty, nothing is stored, the head and tail will be empty. the head and tail will be equal. So usually what we do is we just decide that in this situation right here, where we've got only one spot left, that's when we say the queue is full. And if we wanted to really store something in that last spot, we'll just make the array one element larger. So the is full looks like this. So the next location we're going to add is t plus 1. If next equals 8. In other words, we're saying if we're going to do an add, right, what's the tail going to look like afterwards? So the next t is going to be t plus 1 or maybe 0 if it rolls over. And then we can say if the next t is equal to the head, then the queue is full.
I've seen in multiple implementations some sort of, again, I don't want to skip ahead here too much, but overridable functions where it's essentially like an update loop, where you can just keep adding things to it and it will execute those every so often. I guess what I'm asking here is, when would you choose to do that over something like this, or is it more just a design difference to know about?
I'm not sure what you're describing. Can you try it again?
So, for example, and I'm sure it's the same way in Java, but if you have a video game engine that's using C#, there's some kind of overridable function, like an update function, that will execute every frame.
Mm-hmm.
And you can just keep adding your processes to it. Check if the player is new, check if something happened, right?
Mm-hmm.
Almost acting like this, right? It's going to keep adding all these processes and going through essentially like a circular queue. When would you do this over that, per se?
I think they might be kind of different things, what you're describing and what we're doing here. There's something that feels similar in there, but this is more storing information in this first in first out structure, and I think what you're thinking of, like calling a frame update function periodically, might be something that would be using a queue like structure underneath, maybe.
Okay.
And I think that might be agnostic to how you implement that queue-like structure with a list or with an array or things like that.
Interesting.
Yeah. So modular operator is your friend with a lot of this stuff, right? If t equals 8, t equals 0, we can do the same thing by just saying t equals t%8. Right, and that automatically means, if t is between 0 and 7, this will not change the value of t, because the remainder when you divide by 8 is just the original t. But if t happens to be 8, the remainder when you divide by 8 is 0. So this does the same thing as if t equals 8, set t equal to 0. And we can rewrite some of this stuff like qt++ equals n by doing something like this. Yay. Right, so this says store your thing you want to store at position t in the array, and then increment t, and if it happens to be equal to 8, set it back to 0. So that's a maybe more succinct, but also maybe a cleaner way of describing this operation. and then same for remove, and same for doing these checks to see if it's full. So we could do this check by saying right, if t plus 1 modulo 8 is equal to wherever the head pointer is, then we know the queue is full.
So
You-
this is not just for like processes. This is for actual data.
This can be for anything, right? So it could be processes, it could be data, it could be, you know, an event handler. It could be you're trying to process, you know, clicks from a game controller, and so you want to process them in the order in which they occurred, and so you would, you know, have an interrupt routine. When somebody clicks a button, it fires an interrupt, and you very quickly just take the event and you throw it in the back of a queue. And then eventually, you know, a lifetime later, you know, being like maybe a few milliseconds, something comes around and says, okay, what's the next click that we got from the controller? And it pulls that event off the head of the queue and says, oh, somebody clicked the X button, you know, and you go from there. So we'll find some applications for these. We'll do kind of a bogus application in PA2, right? We'll implement some stacks and queues and just do some stuff with a command line interface, just to work with them and exercise them and help us develop them. But you can use these for a lot of real world things, both low level, you know, inside an operating system, but also higher level things.
So do you think it would be probably generally favored to have to use since we have so much memory to work with nowadays, we can probably just get away with using the array format, right? For most applications.
You can, except for the fact that this won't grow boundlessly, right? This needs you to decide ahead of time. Okay, my queue is only going to hold 8 things, and then I have, you know, this magic number here where it rolls over. And if there's a temporary burst of activity and I need 100 things in my queue, right? I'm stuck. My queue is going to be full, and my software is going to have to crash. And if I know that, you know, once in a while I'm going to have a burst of 100 events, I'm going to have to set up my queue to hold 100 events, and I'm going to be wasting that space most of the time. So a linked list has the advantage that, you know, you can dynamically grow and shrink. It's a little lower performance because dynamic memory allocation and freeing has some overhead associated with it. But it's a trade-off, right? Time versus space. It's the universal trade-off in computer science. If we're really worried about speed, we might go with something like this, or look for hardware support. If we're worried about being able to grow and shrink at will, right, a linked list will probably be fine for us. All right, so that's basic view of stacks and queues, and I'm gonna figure out PA2 probably tonight and try to post it sometime tonight, I hope, so that we can talk about it on Thursday, and I think it's gonna involve, you know, stacks and queues and a command line interface, and then we'll probably put that together with, I mean, so that'll involve using the linked list package from PA1. And then we'll probably put the queues and the linked lists and the stacks together for PA3 and do something with hashes. And we'll be building associative arrays from the ground up in C, and using those to do some more interesting programs. So this is all, you know, stuff building on other stuff. So if you like it, good. If you don't like it, hang out, and you know, we'll be doing different stuff soon. All right, that's all I got. I will let you out 2 minutes early. Have a good afternoon, and I will see everybody next time.
Thank you.
Thank you.
Thank you.
Thank you. Have a great day.
Thanks, you too.